Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good afternoon. My name is Eyal Ofek, and it's my pleasure to invite you to the afternoon session. And the first presenter today is Craig Knobloch from the University of Southern California, when the subject is integrating online maps with aerial imagery.
Okay, great. Thank you. All right, so I'm going to talk about finding and integrating maps with aerial imagery, and I want to acknowledge my colleagues on this. So this is joint work with Sari Shahabi, who's sitting back there somewhere, Yaoi Chang, Aman Gol, Matthew Mickelson, all from USC, and then Jason Chen, who's at Geosymbol Technologies, which is a spin-off company from USC. And this is research sponsored by a combination of the National Science Foundation, the Air Force Office of Scientific Research, and Microsoft Research. So, okay. So here's the problem we're looking at. The first part of the problem is there's lots of information out there. And so one of the things we wanted to do is say, OK, we'd like to go out and find maps that we could actually put on top of imagery and find them automatically. And we can go out to an image search engine like MSN here has an image search engine. And I entered here Redmond Maps. And I get back, as you can see, some things that are maps. Let me try this pointer. So this is a map, and this is a map, but that's not really a map. And so you can see there's some combinations of maps and things that are not actually maps in this image. And so one of the problems we looked at was automatically classifying things into maps. That's the first part of the problem. And the reason we wanted to do that was for the second part of the problem, which is then to take these maps and automatically align them with the imagery. So here's an image that was automatically processed where we didn't have to tell the system anything about the map itself except its general location. So you could get it out of a map search engine. And then the problem then was, could we actually determine the exact coordinates of the map, find the control points, and then superimpose it on top of virtual Earth in this case? So that's the problem that I'm going to talk about today and how we actually solve this problem. And there's really two parts to my talk. First, I'm going to briefly review previous work that we've done on automatically aligning maps with imagery. And I'm going to do this pretty quickly. This is stuff that I talked a little bit about at the last Virtual Earth Summit. So I don't want to spend too much time on that. And then I'm going to talk about the newer stuff we're doing on automatically identifying maps. So let me dive in and start that. OK, so here's the problem, as I said. On the top, we have some image of the world. And at the bottom, we have some map that we found from somewhere. Maybe we got it out of one of the image search engines. And this map, a lot of these maps are in raster format. So we don't actually know the metadata for the map. If you know the metadata, great. You don't need to go through this process. But a lot of times, you might go out and you might find maps about all kinds of different things. It might be layouts or locations of oil and gas wells. They could be real estate type map. Lots of interesting maps that are available, but they're in raster format. And so you don't have any information about the coordinates of the map or even the details like the scale and locations of things in the map. So we want to put these things together so that you get the combination and you can get the information. And many times, one of the most useful types of layers in the maps is simply the text layer, which has all the labels on the roads and buildings and so on. OK, so here's another map. This is a map that we got from the Washington, D.C. transportation website. It's a PDF. There's no metadata for it. You just go there and you can download the map, and it has the location of all the bus lines. And you say, well, I'd like to superimpose that on top of the imagery so I could see the locations of all those things. But you'd have to do it manually today to do that alignment. OK, so what we do is we developed an approach where we essentially use the vector layer, which is essentially the road layer, as the glue to essentially align the map with the imagery. Okay, so the way this works is we start with a map and an image, and we'd like to bring these two things together. And so we also have some kind of road network layer here. And the first step is we have to take this road network and align it with the imagery. And one of the problems that we find is that a lot of these kinds of layers and stuff, they're not aligned, and we need fairly accurate control points for this process. So the first step is to actually automatically align the road layer with the image so that we know exactly where all the intersection points are on the image. The second step is then to take the map and find all the intersection points on the map. And we want to do this automatically. We don't have to go through a manual process where the user finds each of these control points, because it's just too time-consuming to do this over large numbers of maps. Once we have that, then the next step is to actually do a process we call point pattern matching, where we're going to determine the relationship of the points here to the points over here. And in some sense, what's going on here is that we're using the layout of the intersections as the as the key or the sort of the fingerprint of the map to actually figure out the relationship to the image. So we know the general area, that this is a map of some city, let's say, but we don't know the exact location. And so we're using this layout of these intersections. And intersections over a large enough area are going to tend to form a unique pattern. So we're exploiting that property here. So we have a point pattern matching algorithm that comes up with the matching between these, so then we can actually superimpose the map on the intersection, the map on top of the imagery, or vice versa, and do a process called conflation, where you actually stretch the map so it actually fits over the image. Okay, so here's the first part of the process. So the first problem then, I'm going to just very quickly review, is work we published in 2006. But it essentially goes through this process of taking the road network and aligning with the imagery. And the basic problem here is that, as I said, if we just take the road network and just superimpose it on the imagery, it's actually not aligned. And if we go through some automatic conflation process, then the intersection points are actually on the intersections, which is important for the next step of the process. And just to give you a sense, I'm not going to go through the details, but just to give you a sense for how this process works, what happens is we go through a general process here where we'll first identify a set of control points. And I'll describe how that works next. But that's really the heart of the process, which is we find a set of control point pairs, and we're using the intersections on the vector data and finding the corresponding intersections here on the image. We do some filtering so that we get rid of any noise that we might have introduced in this, and then go through that final sort of triangulation rubber sheeting so that we end up with the road network superimposed or correctly aligned with the imagery. So the key then, as I said, is this control point detection. And that process is essentially we start with the road network. And we're really explaining the fact that we don't have to just do road extraction from the imagery, which we all know is hard. Instead, what we're doing is exploring the fact that we know something about the approximate locations of the road network. So it's close, it's just not aligned perfectly. And we also know something about the general shapes of these intersections. And so if the intersection is here, but the real intersection of the imagery is down here, then what we're doing is we're looking for the intersection within some radius of that original intersection. And so the first part of this process is we're going to take the image and do some simple machine learning to basically classify pixels as either on-road pixels or off-road pixels. So that's what's shown here on the right, where we have the white is the road pixels and the black are the off-road pixels. And you can see things like trees create some noise in there, and roofs sometimes look like roads, the usual kinds of problems we have there. Then what we do is we take the vector data of this road network, and we build some kind of template here that we can then align with the image. And now we can combine these two, essentially searching for the best match within some radius of that. And so, that's one possible location. So you can see it goes through a search process and decides that, okay, this is the actual best match of that intersection point onto the actual intersection. So that we can get a nice alignment between those two different layers. And that will then tell us where the intersections are on the image. All right. So the end result, so here's a sample of the result of this. So the red vectors, the original vector data here, I think this comes from the Missouri Department of Transportation. And the blue line here is the actual aligned imagery and stuff. As you can see, the alignment's quite good after we go through this process. We know where the intersections are. Now that brings us, so that we've sort of gotten to this point here. So we've got this image here, and all the little red dots shown there are the actual intersections on the roads. Now we go through the other part of this process where we have to now find the intersections on the map and align it with the image. And just very quickly, I just want to give you a sense of what's going on here. So this in general is hard, and we don't want to have to train this for every map. So the idea is we go through a process where we first do some kind of automatic thresholding where we can pull out the background color and we end up with just all the foreground pixels, which contain the roads and the text. And then we're going to remove noisy information, which in this case is the text. They tend to interfere with finding the road intersections. We go through a set of transformations where we'll, once we remove the text, we end up breaking the lines. And so we'll go through some morphological operations where we'll clean that up and reconnect the roads. We find the corner points where the things that are likely to be intersections. And then we finally have some way of actually testing which things are really intersections by checking how many roads are actually coming together in here. And so what we end up with is a set of detected intersections now, which are actually shown on the map. And there's a whole paper that describes this work, and I just don't have time to go into it today. But I want to give you a sense that this is an automatic process. We feed it in, find the intersections on the map, and now we know where the map intersections are. And the next step then is to do this point pattern matching, where now the problem is that I've got all these intersections here and all these intersections over here, and I need to figure out the relationship between these two things. And this can be a fairly search-intensive process, but we exploit some properties. So, for example, if we assume the orientation of the map, because most maps are oriented north, and if they're not, they usually indicate what north is. So we assume we know the orientation, but we need to worry about the translation and scale of the maps. If we know the scale, then we can give it to the system, but if we don't know it, we can still handle that. And so what happens here now is we essentially take the points from this, and we're going to look for the corresponding matching to the points over here, and find that in fact the best fit for this set of points is going to be right there, and that's going to tell us exactly not only where the map goes, but it's going to give us the scale and the translation for this, and this is very important. It gives us the control point pairs. So if we figured out the mapping was, that means that we know the mapping from each intersection point here on this map to each of the corresponding intersection points over here on the image, and we can use those for the final process, which is called conflation, where we're basically doing this triangulation process in rubber sheeting, where we're essentially taking each of these triangles and essentially stretching them to fit on top of the image. So in some cases, this means we're going to have to drop some pixels. In cases, we're going to have to fill in a few pixels. But the end result might look something like this, where we had that original map, and now we've stretched it to fit on top of the image. This map is slightly distorted, partly because of the fact that there was probably some cartographer involved who moved things around a little bit to make things line up. But you can see the relationship of the bus lines directly on top of the imagery for Washington, D.C. OK, so that's my very brief review of sort of the general techniques we've developed for automatically aligning the maps with the imagery. Now I want to get into the new stuff we've been working on, which is how we can actually automatically identify these maps. All right, so what we want to do is basically be able to go out and harvest these images from the web, or maps from the web, but we really start out with some type of images. So we might use something like the MSN image server, where it'll generate a set of images, and we can specify the area. So one useful technique we use is we often say, OK, here's the name of the city, and then we give the keyword maps, and maybe about half the things it returns are actually maps. And the problem then is we want to basically classify these things and actually generate a database of the maps that then we can go on and do some additional processing. And the kind of processing is exactly what I just described, whereas then we go through those processes of actually trying to pull out the intersection points and then do the alignment. But that's an expensive process, so we don't want to do that on a bunch of random documents, which is one of the reasons we do this classification first. Now, what we assume here is we have a couple of repositories. We have a repository of maps that we've seen before. So we've done a bunch of classification of things that we say are maps. And we have another repository of non-map images. These are things that are not maps. And when I'm talking about maps, I'm talking about street maps. So we usually classify them as, they have to have a road network on them if we're going to classify them as a map. Because there's many maps that just are, generic kinds of maps. OK, so the basic approach that we take to this problem is using what's called content-based image retrieval. And the idea is that we're using the similarity of the image that you want to classify to other images that are in these repositories. And so the nice thing about this approach is it's fast. It's based on sort of information retrieval type techniques. And it's quite scalable. And I'll talk a little bit more about that in a minute. But the way this works is that we go and we use the image we're trying to classify to essentially query the repository of maps and non-maps, and it returns some set of images. And in fact, what happens is the set of images it returns essentially are voting whether or not it thinks this thing's a map or not a map. So this is based on sort of k-nearest neighbor type search. And we compared this, and I'll show you the results. An earlier version of the system we developed using a machine learning technique called support vector machines, and we compare it to the use of SVM in this, and we found that it actually works better. So here's the way content-based information retrieval works: is you have some image set, and you have some query image, and then you use some similarity function, and I'll talk about the similarity function we use for maps in a minute. And you go out and using this image and the similarity function, it goes out and finds those images that are closest to your query image. And it has to rate them based on the similarity function and then returns the closest ones. Now in terms of the features, so we need some similarity function that's going to actually work well on maps. And we've experimented with a variety of them. And one of the ones we found that worked the best is using what are called water-filling features. And you can think of these as sort of similar to water going through a set of pipes, where you have forks in the pipes, and you have some set of flow for the amount of water. That's why it's called water filling. And this works well on images that have a very strong edge structure. And one of the properties of maps that, if you think about a map that you can often recognize, at least a street map from a distance, is the fact that they have this sort of this pattern with lines that are very clear. And one of the advantages of using the edge structure instead of things like the color on the map is that we get this color invariance. We don't want to have seen this map before in order to recognize it as a map. And so we found that you basically have maps of every possible color. And so we wanted to abstract away from the color itself. So here's, so the first step in this, to use this sort of water-filling algorithm, is we're going to run this on what are called edge maps. And so we use a standard sort of vision algorithm called the canny edge detector. And this just shows an example map. So here's a map on the left, and on the right is the result of running the canny edge detector on that. And you can see the edge structure in this map. It's very clear, right? It's really basically a whole bunch of lines that come together at various places and stuff with a little bit of text superimposed in different places. But that's the first step. And then the next step is to actually compute these sort of water-filling features. And so let me just explain the water-filling by example here. So here's just a set of snippets of what could be a map. For a straight line like this might have a filling time which is based on the number of pixels. So if this is 50 pixels in length, then this would have a filling time of 50 here. And then the fork count for this example would be 1. And that's simply because in this example there's no branching. If we go to the next example in the middle here, you can see that, okay, this has an increased filling time because there's more pixels. So maybe you have twice as many pixels. This would give you a filling time of 100. And then you have a branch. So each branch is going to increase your fork count by 1. And so now we've got a fork count of 3. Then on the third example, you can see it's a little smaller, so maybe this has a filling time of 70, but a higher fork count, and you can see that there's more branching in this particular image. In that case, it's 9. So those are what the features are computing. And actually, what we do is we compute these sort of aggregate features based on these water-filling metrics. So we compute 4 things. One is the maximum filling time and its corresponding fork count. So the image is sort of broken up into sub-areas. And then for each of those sub-areas, you're going to find whichever one has the maximum filling time. And then for that one, you're going to compute its fork count. And this is a measure of the longest edge and sort of the complexity of that edge. The second one is the maximum fork count and its filling time. So instead of computing the maximum filling time, we're computing the maximum fork count. And this is going to give us a measure of the sort of the highest complexity of some part of the map, and then its corresponding length. And then we also create this filling time histogram and a fork count histogram for the whole image, and the areas that it's broken up into. Okay, so those are the basic features that get used. Then what happens in the actual content-based image retrieval process here is we started with some image we want to classify, and then what we do is we use this C/R. We have these 2 repositories, the map repository and the non-map repository. And then we use the content-based image retrieval to find the 9 most similar images. I could only fit 5 here, but imagine there were 9. But here, in this case, we returned the first 3, which have been previously classified as maps. So they came out of the image repository, and we already had labels on them. And so it said, okay, these 3 were identified as close. And we also returned these other 2 things that for some reason it decided was close to this. These are non-maps. And essentially what happens is we just vote. I mean, based on what came back. So these 3 are voting for it's a map. These 2 are voting it's not a map. So we decide that we take the majority. And in this case, we say, okay, this thing we're going to determine to be a map. Okay, so how does this compare to doing this in machine learning? So in machine learning, we have to do something similar where we need to train the system. We need to give it some training data. And one of the things that comes up in the machine learning is, okay, how many classes do you have? And we can do it as a binary classification. It's either a map or a non-map. But one of the problems that we had with training the machine learning classifiers to do this was that maps are all you have a huge range of things that come up in maps, and there's a huge variety of them. And that using something like support vector machines, it would end up with either low precision or low recall, depending on how you did the classification, to get fairly high accuracy. So the machine learning is trying to use one model to sort of distinguish the maps from the non-maps, and it was challenging to do that. The other thing you could do would try to break it up into sort of separate models. You say, well, there's different classes of maps because different maps look different. But that requires a lot more work to do the labeling, trying to figure out which maps fall in which class, which is actually quite hard. But we did want to compare it to this. And there's been some related work here. So the SVM work that was done previously for solving this problem on classifying maps was done by another student of mine a few years ago. And here we didn't use WaterFilling. We used a different metric here. We used what was called lost textures. And these really look at the texture map. Again, we're trying to be color invariant, and it's just a different type of feature. That instead of looking at these edge features, we're really looking at sort of the texture type features in the map. Other sort of related work here is the CBIR work, CBIR-based KNN type work, and this was used previously for classifying images in the medical domain. And there, the medical images have very different kinds of properties and stuff, and so we found that the features that they were using didn't work that well in our domain. And then the other piece of work here that's relevant is that there's been a fair amount of work in using WaterFilling features for other applications of CBIR. And so some of these types of things are features that we may want to look at in the future to basically improve how we're doing. But the edge features, we'll see in a second, work quite well. OK, so let me run briefly through the set of experiments we ran on this. So we took quite a variety of maps. So we collected maps for the set of cities shown here. And then we took the Caltech 101 database, which I saw in another talk. Someone else used the same database. But it's a very nice image database of things that are all not maps. And so you can see the total number of images in the repository. It's about 3,000. And then we have about 1,700 are maps. And I don't know how 3,000 that are 400 non-maps. I don't know why those numbers don't add up, actually. But the experiments we ran were to test two things. First, we wanted to show or test the hypothesis that the content-based image retrieval is better than the support vector machines. And so to test this, we wanted to compare them using the same features. So we ran the machine learning stuff that we'd done before using the WaterFilling features. And so we took 1,600 training images. So we randomly picked them from the repository. And then 1,600 testing images, which are distinct from the training ones. And in both cases, we took equal numbers of maps and non-maps. The second hypothesis we wanted to test was that the WaterFilling features actually work better than the lost textures. And so we compared we actually ran both the content-based image retrieval and the SVM on both types of features. The lost textures work terribly on the content-based image retrieval, so we don't report the results here. But we also compared the support vector machines on both types of features. And these are the results. So just a summary of the results here. So in the first line here, we have the CBIR with WaterFilling. And you see this, we got the highest precision and recall. So we have an 82% F measure, which is the combined precision and recall. The support vector machine with WaterFilling, which is the same features we're using here, it was slightly higher precision, but the difference here was not statistically significant. So it's very close. It's effectively the same precision, but you can see the recall is much lower. So it's more than 20% lower on the actual recall, which is really significant in finding the maps. So you can see we end up with a much lower F measure for the results here. The second comparison was, running SVM across these two types of features, and again we can see that the WaterFilling actually helped SVM quite a bit. So we were able to get much better results using the WaterFilling features because the edges really seem to work very well for map type images. Okay, but you could see, sort of in summary, that the CBR with the WaterFilling really worked the best for this, and we're getting pretty good results on this. I think we can do better, so I'll talk about things in a moment, the next steps. But here's just a quick graph summarizing what happens. Okay, on the x-axis here, as we increase the amount of training data. So what's happening here along the x-axis is that we're increasing the number of maps and non-maps that we're training the system on. So 200 here would correspond to 100 maps and 100 images that are not maps, and so on, and we go up. And what we wanted to see was what the impact was on additional training data. The green line on the top is showing the CBR with water filling. The orange line in the middle there is the SVM with water filling, and then the gray is the SVM using lost textures. And so you can see they're all improving with additional training data, although we're only going to get so far. You can see it hasn't quite plateaued, but it's not going to get to 100% using this. So the question is, all right, we started then looking at, well, what kinds of things do we need to do to really get the performance, to get the next level of performance so we get up into the 90 percentile. And one of the things we discovered for a lot of the maps that were misclassified, or images that were misclassified, is that we had these things that we called sort of culprit images. Okay, they were things in the database that would cause the system to misclassify a map. And usually, a lot of these misclassifications were essentially off by 1, meaning that it was really close. Okay, the errors tended not to just be clearly a map or a non-map. Those were easy. They tended to be right in the middle, right? That if there were 9 things we were using to classify it, it would be 5 to 4 or 4 to 5. And what we discovered was that there was a certain set of images in our database that over and over again actually could be held responsible for the misclassification. So here's an example of one. So you look on the left, you say, okay, well, what we see is a picture of a person there. But on the right, you can see that there's this road network behind his head that caused the system to essentially say, okay, these look like roads to me that are being connected up and had similar properties to maps and stuff. And we found a lot of these sort of things that we call culprit images here essentially were caused by kind of features in the background that you wouldn't even necessarily normally pick out. And so one of the things we're planning to do is we have a UI for the system we've been building, is to actually just go back and be able to very quickly look at the images that it's making mistakes on and then reclassify the mistakes, but also start to look for for the ones that it's making mistakes on, look to see if there's some pattern in the images that are causing the misclassification, and then remove them from the repository. Okay, so to conclude here, so we essentially have developed this method for automatically harvesting the maps on the web that's accurate, fairly accurate. I mean, I think there's a lot more we can do in terms of improving the accuracy there, as I said. Fast and scalable. It's scalable in the sense that it's really easy for us to add additional maps to it to improve the overall accuracy without hurting the performance of the system. So future work, we're going to look at resolving these things that we call culprit images, exploring other features. So I mentioned there's other features that people have explored in the past, and so we'll try to incorporate additional features to improve the classification. And then finally plug it into our automatic sort of georeferencing framework, where we can then take the images that are coming back and then pass them through the whole process, where we then pull out the intersections, do the alignment with the imagery, and then we have, our vision then is that you have a whole repository of maps for a given area that you've automatically harvested. That's it. Let me take some questions.
Thank you. Questions?
Hi. In your testing set, the non-map images, most of them were photographs, or some of them were also...
No, there's a whole variety of things. At the Caltech image repository, there's a lot of photographs, but there's a lot of other stuff in there too as well that are not photographs. So there might be paintings and other kinds of things. That repository is available online from Caltech.
I presume a lot of the maps that you find are going to be geocentric. I mean, they're not sort of a spherical coordinate system.
What? Sorry?
Most of the maps you'll find online are sort of generated with digital mapping tools. There's some sense of geocentricity, right? They're on a plane.
Yes.
That's another. Have you sort of considered it as a pattern, as a bias when you're trying to identify something that's a online map? I mean, yeah, you'll find things in strange projections, but most of them, I presume, will.
Yeah, in fact, what would happen with things like strange projections and stuff is that we may be able to identify it's a map, and then we would probably end up failing to, I mean, it depends on how strange it was, but we might end up having trouble. Right. Well, actually, the real problem is that, we have maps that as long as they're drawn to scale, and we can do the processing on the map, we'd be able to actually do the mapping. And one of the things that happens with things like the projections and stuff is because we're not just looking for the corner points of the map, right? We end up finding the control points that in some sense we can actually correct for the different types of projections and stuff. So you'd end up stretching the map. If you could find the mapping, you'd end up stretching the map so then it would align with the image that you were looking at. The real problem comes up in the class of maps that are out there that are not to scale, for example, right? That there's going to be a whole set of things, or one of the things we haven't dealt with yet is dealing with maps that are really high levels of abstraction, right? So you're only seeing sort of the very high-level road network and those kinds of things. So those are the places that we're going to get in trouble. But any other questions?
Anyone else?
Okay, great.
Okay, thank you. The next speaker is Horace Bishop from Graz University of Technology, Austria. And the subject is semantic enhancement of street-side imagery and enrichment.
So thank you for this introduction. So, light? Is there someone turning on the light? Okay. But I don't want to fall you asleep, huh?
That's okay? More?
I think this is fine. Okay, so. Okay, so thank you for inviting me here and giving me the opportunity to talk here. I have also to thank the Microsoft technical support that saved my talk because my laptop crashed, and unfortunately they were good enough to get off this data from the laptop so that you see a presentation here. So it's really great. Otherwise, I would have to give a presentation without slides, and this would be less interesting. I hope so. Okay, so what I'm talking about here is semantic enrichment of street-side data. And this is work we have done recently. So you have seen here a lot of presentations like Steve Seitz, Steve Stansel showed like what you can do with now this technology generating massive data. So go there, take photos, do 3D reconstruction like here, and you get various sorts of things. But, and I have to thank Wolfgang Walker for his presentation yesterday because he paved my way. This is just data. These are triangles, points, pixels. You can nothing do with the data except looking at it, navigating through it, browsing through it. And Wolfgang had some nice examples yesterday where he showed, well, what you really want to do is you want to query this data. You want to ask questions. Where are the windows? Where is the parking meters? Where are the cars? Where are the trees? Find me a building close to a tree or close to 3 trees, which means we need some semantics there. And Wolfgang had this nice red line there and said, well, we need to cross this red line. And I hope to show you something how we can do that with some of the technology. Of course, I'm not saying we have solved that problem, but I would like to give you some hints how we can do that. So, as I said, data isn't enough. So we have to recognize objects. And I will show you something on street-side data we did recently. So the talk will be split in 2 parts. I first spent briefly about recognizing compact objects like cars, pedestrians, or as you have seen probably in the demo, these parking meter things. So where you have really compact things. So this is type of street furniture you would like to recognize. And I will talk very briefly about it and show you how we can do with one of these approaches we have recently developed, like online boosting. The second half of the talk will be devoted to recognition by shape. This is very recent work, basically done by Mike Donoso in his PhD thesis, where we have developed a new efficient shape matching method called IS match. And I will show you how this works and explain you the algorithm. And then I will show you some recent results we have done with that on window detection, which is one of the things you really want to do on street side images. OK. Before doing that, I would like to report you an additional success story we had recently. Because one of these goals of this Microsoft grant is also to foster additional research. And we have been very successful in that. We have been recently granted a project for a grant from the Austrian Ministry of Science for a project called CityFit, which stands for High Quality Urban 3D Reconstructions by Fitting Shape Grammars to Images and Derived Textures from 3D Point Clouds. So a long title. So the story is you really want to generate building grammars from data you acquire from things. And this is a 3-year project with the partners Microsoft in Graz, then a Computer Graphics Institute in Graz, and our institute in Graz. And the total project money we get for that is more than 600,000 euros. And with the new euro since the dollar is so weak, this is more than $1 million. So this is quite some money. So basically, if you calculate what you invested in this research grant, it gives you the factor of 25. So for $1 you put in the research grant, you get now $25 back. So this is worth the money, I guess. So the challenge we have here is we really want to do building reconstruction, building grammars for also these old type style buildings where you have really a lot of facade structures, very detailed facades, and you would automatically derive grammars that construct you that building. So this is a real challenge, and we will keep us busy at least for 3 years. Probably we will longer. But this is the goal we have, and this is some of the data we recently acquired in Graz. And another nice thing is this project, so there's a competitive call where I think there were about 30 submissions to this call, and only 7 of them were granted, and actually we won also the first prize. So this is the certificate that stands like first prize, so erster Platz in German. So quite successful project. Okay, so this was somehow the advertisement. Now to the real stuff. Let's talk about recognition of compact objects. By compact objects, I mean objects which I can recognize by their appearance, where they have a compact shape, so like rectangular type shape, not sort of spread out in space. And typical examples would be cars, parking meters, signs, lamp posts, something like that. And so a common approach of doing that in the machine vision literature is like you take some features and then you use a classifier to do that. And typical examples we have also seen in the talk before, but Craig, like you would use, for example, SVM, support vector machines, to do that and classify that. Or other approach would be like boosting type of methods to do that. The problem with that is if you follow that thing, you need a lot of training data. And we know from the literature, when you have enough training data, these things work nicely. So if someone is sitting there and labeling you 100,000 cars and 100,000 non-cars, perfect. But of course, we have a lot of street furniture which we would like to recognize. So maybe you find someone doing you the cars, but you don't find someone doing you all the parking meters. You don't find someone doing all the lamps and all these things. So one of the goals we have here is really reducing the training effort. And by doing that, we have developed over the years a method called online boosting. So maybe you're familiar with these Viola-Jones type boosting things, which have been very popular in the vision literature. So what we can do on top of that is we can incrementally and online train such a classifier as new data arrives. And using the right features, basically things that can be calculated very fast. Typical examples would be these Haar wavelets, integral orientation histograms, local binary patterns. Basically everything you can calculate fast with this integral data structure, you can do this in real time. So this is one of the advantages. And basically what we are doing is here, and what we have shown in the demo and in the poster, we are putting this booster, since we can do it now fast, in an active learning framework. So we have images we have that online booster run the booster, get some detections, and then we have a teacher, in this case a human, that says, well, this is correct, this is not correct, and this provides the labels, and so we then finally end with a classifier. The big advantage of doing it that way is you only label the necessary data. You don't label unnecessary data. So this really reduces the labeling effort quite a lot. And here are some examples, and you have probably seen in the demo. So here are parking meter images. So if you look closely, so they're quite dark. Like here you have this type of parking meters we are interested in. And of course, this look in every city, they look different. So you really have a demand on, so you cannot build one universal parking meter detector. Every city has to be its own. So at least there must be some training effort. So if you click once, this is basically, say, like, this is a parking meter, then this is the positive response you get. Then you say, well, this is wrong, this is wrong. You click a few clicks more. Then you see you detect it, but you still get some false positives. And as you go along, the number of false positives reduces till you then finally end up with a perfect detector. And basically, if you do this, so on this type of images, it basically means like 50 clicks, and you have already a fairly good detector, which is much more efficient than doing that offline. So this is one of the examples. We have been also using that on aerial images, also from this Vexel camera, for car detection. So basically here you see cars, and one of the goals is to detect the cars, and either for removal or counting. And so training with one example will give you a lot of false detections. 10 samples, 50 samples, you always get a perfect car detector. And yeah, so then doing some post-processing like mean shift gives you a perfect car detector. So this is a very universal tool which you can now use for these different type of things. And Wolfgang, I hope you're happy with that. You see that this is something you can do with.
Can it be part in any direction then?
Sure. So this is one of the tools we have developed for this type of compact object. Let me now come to the second part, which is about shape matching. And shape is another very useful tool. Not all of this object can be characterized by appearance, by texture things. Like looking at this type of images, we as humans are very good. We see this is a face, this is a horse, this is a plane. And the only feature we have there, despite of all these occlusions and these things, is shape. And so what we are interested in, we need a partial shape matcher, so a matcher that also works when we have partial segmentation occlusions and that thing. And since we want to apply this on lots of data, meaning street side data, it has to be efficient. So this is the goal we set up. So what I will present you is this IS match that can match this type of shapes, even if they are occluded, and give you perfect shape matching. So the IS match basically has this type of characteristics. It uses sampled points. So the shape representation is just you take your points and you sample on a regular basis along the shape. So you don't have to detect like high curvature points or interest points along the shape. You just do regular sampling. It exploits the neighborhood information, so the point plus its neighbor. So this is related to the shape context thing. But it allows also for occlusions, which, unlike shape context, which basically it puts a histogram representation of that, cannot do that. And it's really efficient. So the goal is to provide competitive matching results compared to the best shape matchers that are around, but at reduced computational cost. How we do that, I show you. So basically, the IS match consists of 5 steps. The first thing is we have to select the shape representation, and as I said, we just sample points regularly along the contour. So you have the shape here, and you just pick points and say, like, I want to have 30 points along this contour, and you sample them. So this is straightforward. Then the second thing is shape description, and I show you how we do that. Then how we do the matching, and the strengths of the detector is really in these 2 parts. We have a redundant shape description together with the shape matching gives you really the power of that. Once you have that, the second step is you have to calculate the similarity measure. How similar is your shape to your target shape? And then finally, you could also like do shape completion by once you have the matches, you transform your target shape to the shape and then complete the shape. But this is straightforward, so I will not talk about this thing. So I will spend time on these 3 points. So how does the shape description like? So remember, we have an ordered sequence of sample points along the shape P1 till Pn. So what we do is we take a point on the shape. Then we take all the points along the shape, so this Pi, Pj, and we take a point that is minus delta points away from that shape. And we take that angle as a representation. And so basically you start here at the first point, get this triangle here, first to the first, of course the angle is 0, and then you move delta away, so you get here this angle which you enter here. Then you take the second point, third point, so you get one line here. The same thing you do with the second point, you get another line here of angles. So this is a chord representation. Another possibility, instead of taking the angle, you could also take the cross ratio of the lengths of these chords here. The only parameter you have here is this delta, meaning how far you're away from that thing. And this is basically like a regularization parameter. If this delta is 1, so you're going just like 1 point away, you're finally getting all the fine details. If you take delta larger, you're coarsely sampling the shape. So you end up with a matrix A with all these angles. And this is a over-complete representation of the shape, because basically one line would be sufficient to reconstruct the shape. But you have many of these things. And this is very important that you have this over-complete, because in other shape representations, what they would do is they would put a histogram on top of this type of things. But of course, then you can no longer handle occlusions because you're mixing up these things. So the important thing is that you really have that here. So you have that matrix, and of course, depending on where you start, this matrix will look different. So if the first point you start 5 points far away, this will be a different point. But important thing is that the matrix is just a circular shift of the matrix you would get. Since you're taking angles or cross ratios, this is invariant to translation, rotation, and scale. So yeah. So the next step is how we do. So we have now a shape representation of that matrix. So how do we match now two shapes together? How do we? Since we have these ordered points here, it's basically just an order-preserving alignment of the shapes. So we have this order of points. So we need to solve this order-preserving assignment problem. So formulating that mathematically, so here is this angular matrix, here is this cross ratio matrix. So you can either deal with one or can use both of them. So this is not important. So what you're doing is you try to find you would like to minimize this measure, which basically means you're trying to find submatrices that give you the minimal distance of these two shape representations. Doing that, it basically means you have to loop over three different types. You have the sequence assignment, you have the starting point, and you have the chain length. So if you're doing that in a trivial way, you would have to program a loop over 4 chain lengths, 4 starting point over sequence assignment. So this is a complex process and will take forever. But now we can make use of one thing is we can basically think about these integral data structures because basically what you're doing here is just like putting sums over these submatrices. So looking at this matrix, what we have here. So everything with this A sub means you're calculating here sums over some submatrices. So if I'm now putting this thing in an integral data structure, I can calculate the sums very efficiently just by lookup. So if we now, for each starting point, we calculate such an integral thing, we can very fast calculate these differences, but just look up in these shape matrices. So this allows a very efficient descriptor calculation. So we're getting rid of two of these inner loops there. So we have only one loop related there. It's just the starting point. So we can calculate it very efficiently, the shape matching measure. Yeah, and that's basically the whole trick around that. So you can calculate that thing very efficiently. And here you see some of the results. So this would be the target shape, and here is the align shape, and you see here this is basically the shape, the subshapes that match along this contour. Last point is shape similarity. You need somehow to assess how similar two shapes are, and what we did here, we just borrowed this measure that Serge Bélanger used in this shape context. So he has like these 4 different types of measures. So the descriptor difference, this is what we calculated before. Then once you have this alignment, you can basically put the shapes on top of each other. So you get this Procustus distance. You can account for nonlinear alignments by calculating a thin plate spline energy and also penalize for short matching sequence. So this is basically what Bélanger used. So we borrowed just that measure from him. OK, the question is now, how good does this perform? So there are a few standard databases of shape, and we performed some comparison on that. So there is one, KEMA 25, which consists of 25 shapes in 6 different classes. And here you see some of these algorithms that have been proposed in the literature. Basically, so this matrix means like the first shape, how often did you retrieve it correct? From this 25, we got 25 correct. And as you go along, you see. So this is a very simple database. You basically get perfect results out here. Here, this KEMA 99 is a more complex database. And currently in the literature, this Felsen-Schwab type algorithm is considered to be one of the best shape matching results. And you see we're basically close. So the first 4 or 5 retrievals are as the same as Felsen-Schwab gets, and here in the later things we get a few mix-up. But basically we'll perform as good as him. The important, so this is then, there is another database, this MPEG-7 database, also standard space database. And so here again compared our method to this type of shape. So we're a little bit worse than this Felsen-Schwab, but there are these 2 shapes where our method is extremely bad, so this gets wrong, because you have just this inner structure which we don't account for. So if we remove this, we're basically close to that thing. So basically the results are more or less the same, but the important thing is when you compare the timing. So we've seen like this Felsen-Schwab is basically performing best. So it needs like half a second on this thing. We are needing just 25 milliseconds using 30 points. So this is really a speed up you get here and get basically the same performance. Once you have that, you now can play a lot of different things. So now we have an efficient shape detector, so we can start doing object detection based on shape. So basically, how you do that? Well, you have this target shape you would like to detect. Let's suppose this bottle. Then you extract boundary change. You connect boundary change a little bit together so that you get longer change. And then you basically use the shape matcher. And then you use these matched shapes for center voting, like a half transform type of voting, in order to do this object detection. So we run this on this. So this is basically, so you have that image, you get edge detection, you do this boundary chaining. So you see a lot of clutter, these things, and this is basically what the shape matcher then delivers you as shape matching results. So we have been running this on this ATH database of object detection they put there. So they have this nice Apple logos there. So we see basically what the detector delivers you. So you detect the bottles, giraffes, and these things. So it performs. So we haven't done really a thorough evaluation on this type of database, but it gives you quite some good detection results. Especially these Apple logos are nice because they are so distinct compared to the other. And you see your invariant to size translation, also affine transforms, a little bit non-linear transforms. So it gives you quite nice results. we have also applied this to window detection, because a window can be described by shape as a rectangle, so a very primitive shape. And we have applied this to recently acquired GRADS database. So the thing we have done here for preprocessing is we have used these MSERs, these maximum stable extremal regions, for segmenting that image in two parts, and then taking the contours of these maximum stable extremal regions and plugged it into the shape matcher, and the matching shape was just a rectangular to that. And these are typical results you get. So you see you detect most of the windows. There are some false detections, some you miss on the border. But overall, these are quite nice results. So here are some videos. So if I can. OK, no, this doesn't play here, so I have to show you outside. So running along the facade. So here you see these windows that are detected on this video. And you see basically almost some of the windows you miss. But if you miss the one or the other, it doesn't really matter, because you can simply, by sort of drawing, so if you miss that, it doesn't matter, because you can simply complete that by knowing that left and right there are windows. You just simply can augment it. So this would be one example. Here is another example. So you basically see you almost get really nice window detection results from this approach. And of course, you can get that very fast. So here is another video. And you see few of them you miss, but overall the things look quite OK. So we're quite confident that we can get fairly good detection results. OK, so let me come to a conclusion. So what I have shown you is we have a lot of recognition machinery available, which we can use for street-side data to recognize what is of interest to you. And we have heard during the summit that there is quite a lot of things to recognize there. So, of course, these things need to be combined in a workflow. There is also 3D data available that can be used. Of course, this window detection, you don't need to work on distorted facades, because it's very simple to align them. You can use 3D data. You can use more information, which just would increase the recognition results. And a lot of these things we will do in this new project, CityFit. So thank you very much for your attention.
Questions? OK. So ask. So where does it fail? I mean, it seems like on one, if I'm looking at the Apple, for example, you managed to match under a very strong perspective projection there.
Well, it's not really perspective invariant. So if it's a little bit tilted, so it's OK. There is another thing which we still have to work on at the moment with just getting the largest shape match. So, but of course, if you have like in the middle some occlusions, what you would like to have is like two matches on the top and left. So we need to do some reasoning on top in order to find really the complete shape, because at the moment we're just getting the longest segment that it matches. But we have some ideas how to do that.
OK, thank you.